Hopefully you're in the right place. We've got some really good speakers for you today. First up is Michelle Thompson, who is a former Qualcomm wizard working on Global Star and cellular handset semiconductor design. That's my words, not hers. She is now a co-founder of the Open Research Institute along with Bill Hilbert and Bruce Perrins, and she's going to talk to you a little bit about ORI. Michelle.
Hi, everybody. Okay, so first, some bad news. Bad news. Okay, so communications is a solved problem, right? We're all done? Right. No? Okay. But you know, I mean, we have forward error correction coding that is at or near the Shannon limit. Yeah, right on. Big cheer for us. We have radios, pretty straightforward, simple radios that are autonomous receivers that within 40 samples of an unknown signal can identify them. That's pretty cool. You don't even need to tell it what kind of modulation it was. Not bad. You can talk to almost anybody in the world, right? People are reachable. The number of connected devices has outnumbered the number of people. The number of connected devices on the planet is growing 5 times faster than the number of people is growing. And that was in 2014. So what are we doing here? What are we doing? Well, all of these systems that can do these amazing things are really complex. Typical commercial digital system is almost impossible for a single person to hold in their mind, to understand, to deploy, to experiment with, or to test. So the real innovation, we think, especially in software-defined radio, is, well, maybe not so much the engineering itself, but the way that we do the engineering, the way that we work together to make amazing things happen. And so that motivated me and Bill Hilbert and Bruce Perrins to found Open Research Institute. So I have handouts in the front and a cute little postcard. We are totally devoted to making open source, software-defined radio wonderful things happen. So I know all of you are interested, would like to see more open source work in amateur radio. That is our mission. Now we're a new corporation. We were incorporated in March of 2018. We've applied for 501c3 tax-exempt status. We're not new at this. If you're not familiar with Bruce Perrins, he has a Wikipedia article, so look him up. And Ben Hilburn is the president of the GNU Radio Foundation. So if you're not familiar with GNU Radio, it's an open source, free and open source, digital signal processing toolkit for software-defined radio. You have a software-defined radio? You want to tell it what to do? GNU Radio will help you. Anyway, Open Research Institute is here to help you. Please reach out to us. Let us know what you're worried about, what you'd most like to see in the open source software-defined radio amateur community, and we're on it. Thank you.
Thanks, Michelle. She's going to hand some of this material out if you want to look at it. Okay, next up is Steve. What's your last name? Remind. Brightman. Yes, I keep forgetting. Okay, Steve is a veteran of the semiconductor industry, having worked at TI, Dallas Semi, and Maxim. He's worked on RF circuits for consumer TV and radio applications, as well as mobile applications and devices and satellites. A longtime SWLer, he promises he will get a full ticket one of these days. Is today? Not yet. Okay, all right. Steve's going to talk to you about an introduction to software-defined radio. Thanks, Steve.
Some people call it experience. I call it old age. You have to put glasses on and do anything. So it's not raining outside right now. So a lot of people are not in here just to get out of the rain, which is good. Historically, I am always put on the agenda sometime in the afternoon. So I'm kind of used to people coming in with their lunch or having just finished their lunch and then their eyes closed. They get the siesta thing going. So I never take offense. It's not that I'm that boring. But we'll see what I can do. The first speaker was remarkably brief and succinct. And you thought, that's good, we're not going to get bored today. Well, if I got news for you. So, I didn't really know what kind of audience we're going to have here today, so can I have a quick show of hands? Who owns the software-defined radio? Okay, so I normally give a talk called Introduction to Software-Defined Radio. I've got a field of experts before me. So which one of you guys wants to come forward and give a presentation? Because I'm not claiming to be an expert on SDRs, but my normal role in life is to be an evangelist for SDRs. Anyone that is just interested in it, and usually, is there anyone here that, because I was overwhelmed by that sea of hands, is there anyone that's here just to try and learn something about SDRs? Okay, so you guys will count. Thank you for being nice to me. So, to try and get this within the time limit, I really kind of cut back on this, and I was instructed that I'm not allowed to do commercial messages and heavily promote my products and stuff. So I'm going to see how far I can get before Mr. Hicks beats me over the head. So briefly, what is an SDR? And you can read the words. I don't like reading words on slides because, like I say, my eyes are bad. I can't read them anyway. But basically, the whole name of the game here is you want to take a conventional radio with all those mixers and all this other stuff, everything you did in hardware, essentially you're going to split the task in two. And like almost everything else in this DSP world, the goal is to take the signal, get it from the antenna and digitize it, and then do magic in software. Right? I mean, that's the whole basis of every DSP application that's out there. It's not quite that simple, as people have discovered. There is still a need for some good, honest hardware analog engineering in the front end. You need things like band select filters and all sorts of good stuff. You've got to make sure that you don't get overloaded with exceedingly strong signals and so forth. But basically, the task is get the signal, get a clean signal, as soon as you can, digitize it, and then put it in software, because everything is possible in software, right? If you want to screw something up, do it in software. So why do you want one? And again, because of time constraints, I'm not going to go into great detail on anything. But what I used to do at my pitches, I would sort of reveal these one at a time, like being on the show or something, top 10 reasons. But in general, SDRs give you great general coverage. And I mean, you're not hampered by the fact that you've got a hardware limitation. The guy has designed the radio to be in a specific band or do a specific thing, so you've got true general coverage. One of the key areas that a lot of our customers are using it for is to implement a panel adapter of some sort with an existing rig. And it gives you incredible freedom that when you're working a particular band, instead of turning the knob to try and find someone else calling CQ, you can just look at the spectrum and see where somebody else is. If at least you've got a cap control on your rig, then at the same time, if you see someone suddenly pop up on a different frequency, you click on the display and boom, it'll tune your radio to that frequency, which is kind of fun. The other way is you could be working, say, 20 meters, and you can keep an eye on what's going on in 40 meters. So if the band starts to come alive, it's like, hey, something's going on in 40 meters now, so you just click on the display and boom, you're off working a different band. Audio and IF digital signal processing. Again, I already mentioned that. Everything is done digitally these days. It gives you a lot of freedom. You can do much better filtering. You have the ability to do future upgrades and all sorts of good stuff. Filters is a key thing. In a lot of the software now, you have the ability to put very sharp roll-off filters, which means if you get adjacent signals coming in that are a pain, you can have a very sharp cover for the signal you want to get versus the signal you don't want to get. You can implement very sharp notch filters, so if there's some sort of interfering signal in the band, you can get rid of that. How am I doing for time? Am I good? Good, I'm almost finished. Okay, got it. The key thing for us is, speaking as SDR play, we try to do hardware that works with off-the-shelf available PC hardware. Okay, so you're going to run the software on a standalone PC. It could be still running XP even. But there is a lot of horsepower available relatively cheaply from the PC world because of the economies of scale. So we're kind of riding the coattails of that so that you can buy a lot of processing power, you can run lots of different receivers, you can do all sorts of things at the same time without breaking the bank. Multiple VFOs, that kind of goes without saying. Most radios will give you 2 VFOs, right? You've got pretty much an infinite number once you're doing this in software. You have the ability to record large bandwidths of data. And I'm not going to go into IQ streams and all that other stuff, mainly because we don't have time. Actually, not mainly. One reason is because we don't have time. mainly because I don't fully understand it. But if you want to know all about IQ, Mr. Hicks is your man, okay? But you have the ability, and again, in the case of our receivers, we typically monitor up to 10 megahertz of bandwidth at the time. So you can record an entire 10 megahertz of bandwidth over a certain period of time, and then you can come back later, play back that signal, and you can tune across that band. So if you suddenly see a signal now, you can go across that band and tune as if you were doing it live. Now, I think that kind of takes the fun out of some contesting type stuff, where people will do that. Another thing people will do is they will record chunks, just before and just after the hour, so they can go back and look at signals and try and find out the identification of what those signals were. So that's pretty cool. Record and play back of audio, that's pretty straightforward. You can do that with any Windows kind of software. And when I go around and I talk to a lot of hams, what they're interested in is getting into something new. I mean, you all know now because there's dedicated hardware out there supporting various digital modes, but a lot of people are old school like me. And, we used to just good old-fashioned analog stuff on 20 meters, 40 meters, whatever, doing a little bit of shortwave listening. And they hear about all this other weird stuff that's going on. And an SDR is an easy way to get into it. There's a lot of freely available software that lets you go in and explore digital modes. I'm not going to go into the rest of it. I got a few examples. And then the main reason I tell everybody when they go to these conventions is, well, of course you want one. Can you ever have too many receivers? Come on. So just very briefly, here's some examples of what people have been doing with our hardware. Our hardware is, compared to previous companies, very low end, okay? This is using our RSP1. So we're picking up the NOAA weather satellites on 137 megahertz. People use things like turnstile antennas and stuff. In most cases, you don't even need to use an external preamp. You can do this out of the box. And here's credit to a couple of people that are on our Facebook group, and here's some examples of the weather satellite pictures they got from it. Other examples, and again, I apologize if I'm telling you guys what you know already. I'm kind of looking for the people that don't necessarily know this already, that are trying to get an idea of where they can go with this. FLDigi is another popular digital decoding software that's out there, and WeFax is another one. It's kind of been, WeFax is kind of old hat now. We've got these fancy satellite images, and some of the newer GOES satellites are up there. We're seeing whole Earth full color pictures of the planet, and it's absolutely awesome. One thing we've got demonstrated over in hall number 3 is ADS-B, which is monitoring transponder broadcasts from aircraft. They come down at 1 gigahertz, and they tell you things such as altitude, speed, heading, N number of the aircraft, and so on and so forth. And using this dump 1090 software, you can get that, hook it up with something called VRS, Virtual Radar Server, which will take the information, present it nicely, and show you on a Google map representation of where the flight is and where it's going, which is pretty cool stuff. At least I think it is. So that's what you can do with it. And you may have known that already, or it may have given you some ideas. And then the question is, how do you decide which SDR to buy? Well, the simple answer is, I'm here from SDR Play, so buy one of mine. But, you might also want to buy something from Flex. I see ELAD's here. There's, I think AirSpy's here as well. There's a lot of manufacturers out there. So how do you decide what you want to do? And as I said at the beginning, my main role in life is to be an evangelist for SDRs. So what I always tell people is, when you leave this hall, please go out there and buy one. And I honestly don't care whether it's one of mine, or whether it's one of Steve's, or whether it's one of somebody else's. Because I guarantee you get your feet wet in SDR, you're going to have so much fun. You're going to pursue it. You're going to go further. You're going to get more specialized in what you're interested in. You'll probably go in and identify more expensive hardware you want to pursue your hobby. It's just like any other hobby, right? And yeah. So computers, ham radio, same difference. So some of the things you want to look at: frequency range. Okay, over what range can you tune this SDR? And they're all over the shop. My products tend to fall in the sort of general purpose, all trade things. We can tune from 1 kilohertz all the way up to 2 gigahertz. There are some that won't even tune HF, then it's like VHF and up, and you need extra hardware to get down into the HF band. So just be sure that the frequency coverage is adequate to match what you think you're going to be doing initially. Okay, I started, right? I wanted to do shortwave listening. That wasn't until I discovered all the cool stuff that's going on in VHF and UHF and so on. You'll get hooked, I guarantee it. ADC resolution. There is more bullshit talked about ADC resolution than just about any other subject in technology, I think. Suffice to say, as I said at the end, higher is usually better. I will guarantee you, if you buy an 8-bit dongle in the flea market, it will work. It may not work superbly well, but it will work. I guarantee you, the more bits you get, the better it will work. But that's not the whole story. ADC resolution will affect the dynamic range you have, whether or not you overload the A to D when you're demodulating it. But it's not just the ADC. There's signal processing in front of the ADC that affects it as well. As soon as you put a variable gain stage in front of the A to D, you're effectively adding more bits of resolution. So it's a very convoluted thing, and all I would say if you're coming at it from the first time is, in general, more bits is good, 8 bits isn't enough. So 8 plus is a good starting point. Pre-selectors, I kind of got into that just now. Analog filters in front of the A to D are very important. Okay, what happens is, we're talking about wide coverage receivers here. So the front end of this thing in general is wide open. And you don't want somebody, if you're trying to monitor 40 meters, and you've got some Yahoo with a 2-meter rig standing next to you, pumping tons of energy in there, you don't want that pushing up the signal and overloading your A to D, right? So you need some form of pre-selector in there that narrows down the frequency of interest that you're going to tune to. So that's a good thing to have. Instantaneous bandwidth. The range you can tune over is one thing. How much of that range you can see at any given time is another. So that's what I mean by bandwidth, and I'll show you more about that. Software, there are lots of software packages out there. Some people like to use packages they're already familiar with, and so they would like to use that regardless of the hardware. But most manufacturers will also offer their own kind of software. There are even some out there that have a transmitter as well as a receiver. That is a big debate that we can have forever on the desirability of that. And finally, price. Now, what I've noticed about most hands, and at the risk of making a sexist comment, the amount of price or the amount of money they can spend on a new rig is inversely proportional to whether or not their wives with them at the time. But if it's consideration, be careful. I'll probably get fired for that now. Politically correct, police will get me. So I just wanted to cover that instantaneous bandwidth thing a little bit more. These are some of the parts we've had over the years of SDR play. And typically we have this 10 megahertz chunk that you can imagine sliding up and down anywhere from 2 gigahertz to 1 kilohertz. And that's what you see on the screen at any one time. That changed radically today. Shameless commercial plug. We just introduced a new product, the RSP Duo. And what's good about that is it actually has 2 slices. So you have 2 independent slices of spectrum you can tune, again, over 1 kilohertz to 2 gigahertz. So you can simultaneously monitor 2 frequencies that are well apart. So you can do 20 meters and 2 meters at the same time. Pretty cool, I think. So in general, and I can't speak for other people's products, but I see the industry as being split into 3 broad categories. There's the starter products, bottom left, the 8-bit dongles. They're very cheap. You can get them as low as $10. 8-bit resolution. It's a good way to get your feet wet. And they'll work. And that's fine. You start with that, that's cool. Then you get these general purpose ones, and that's kind of where I'm sitting, which tend to be, they're kind of like the jack of all trades, kind of SDRs. They've got broad coverage, pretty good performance. They tend to be in the $100 to $200 price range. And again, that's another way to kind of get used to what you want to do. And then if there's a particular area that you want to concentrate on, then there are these high-end ones, okay? And they can range from hundreds of dollars up to thousands of dollars. And they'll give you the absolute highest performance level for what they do. And if that's what you need, then that's where you need to go. So, yeah, I guess, Steve, you fall in that category. Right? You build very high-end radios. They're really good and everything. And, of course, you pay for it. So that's kind of the variety that's out there. I haven't talked much about software because, again, it varies as a function of what hardware you have. Steve's radios, that's like called Power SDR, right? Is yours? Smart SDR. Smart SDR. Who's got Power SDR? They did too. That's you? That's us. Okay. So we've got one called SDR Uno, which we show here, and free software that's very popular, SDR Console. HD SDR, cubic SDR. Actually, cubic SDR is pretty cool because it's the only truly multi-platform one out there. So that runs on Linux, Mac, Pi, Raspberry Pi it runs on. I think there's even an Atom API we've got for it now. But in general, the manufacturer-provided software will eat the maximum performance out of the hardware. So that's really all I can talk about while trying to be general and stay within the time constraints. What this picture is showing you here is this is SDR Uno running 2 virtual receivers, and then we've got some digital decoding stuff going on here as well, WSJTX and so on. So I don't know if I've accomplished what you wanted to hear, because I wasn't really sure who you were and what you wanted to hear. But again, I'm here to evangelize software-defined radios. As a shortwave listener of old, it kind of galvanized my interest in looking at other frequencies and having a lot of fun. And I encourage you to do likewise. So with that, I would like to say thank you very much. Another shameless plug. We're demonstrating all that good stuff on the HRO booths in Building 3. Thank you very much.
All right, next up we've got a duo here. We've got Dominic Still, who is a senior security researcher at Great Scott Gadgets, where he writes software and firmware for open source hardware. His primary focus is sniffing and modifying communication protocols. And along with him is Michael Osman, who also talked here last year. Michael is a wireless security researcher who makes hardware for hackers, best known for the open source HackRF, Ubertooth, and Great Fed projects. He founded Great Scott Gadgets in an effort to put open source hardware into the hands of innovative people. Take it away.
Thank you, Steve. I'm Mike, this is Dominic. We're just seeing if we can get video going here.
You succeeded last year.
So this talk is going to be a little bit different. I think Steve put us in the middle because we're the comic relief. This. So here we go. Maybe, almost.
Yeah. Wait.
You know, read the fine print, accept the terms and conditions, and there we go. Ridiculous radios. We are here to talk about some hardware design and software that goes along with them that allows us to do some crazy things, making various projects that we've had going on lately at our lab, where we play with silly little circuits to do radio stuff. And you know, you might call this talk "Ridicule Us" radios, because this is going to be a whole lot of nonsense.
Yeah.
Yep.
If they turn them on,
Does it work? Okay, so we got it. All right. Yeah. Wow. Yeah, it's only just dawned on me that this is specifically a software-defined radio forum, and we've come to talk about hardware. Which is
but some of it's SDR.
because most of what I do is software. Bear with us. We've got 4 radios to show you, and hopefully they're kind of fun and they'll get you thinking about weird ways that radios can work, and also weird radio artifacts of other hardware decisions you might make. We're just going to upfront thank 3 people. Mike Walters, who actually gave us all the idea for one of these and implemented it. Taylor and Jared, who are both back at our booth right now, looking after it so we can be here. And Taylor built some of the hardware for one of these and was involved in some of the other discussions. So we are not standing in the right order for this, but Mike and Dominic have gone through that. We're at booth 5008 in the Hertz building. That's the one just over there. Come by and talk about this way. Oh, wait. I have no idea which way we're facing. It's behind me, but it's the Hertz building. It's building number 5, booth 5008, and it's next to Tapper. And come over and talk to us about SDR or these silly hacks at any point over the next couple of days. Shall I start with this one?
Sure.
Okay.
Let's start with this one.
This is a 433 megahertz on-off keying radio. So the kind of thing you might use to talk to those like wireless home automation things, your garage door opener, or anything like that. And a lot of people want to hack on these, and we've got various products that people use to hack on these radios. But a friend and I were hanging out at a conference once, this guy Mike, and we were playing around with this Great Fit, which is a microcontroller board that Mike's kind of waving at the moment. And it's just a standard microcontroller. There's no radio element on it or anything. And we're playing around with trying to develop some firmware for it. And we're looking at how the internal clocking works. We need to drive a peripheral internally. Don't worry if I'm losing you in firmware development. These details are not necessarily important. But Mike identifies, well, we can examine the clock coming out of this thing because we just direct it to an output pin. And then he attaches the wire to the output pin. And it's like, oh, look, I don't even need to hook up to it to measure it. I can just measure it with my HackRF. At which point we said, well, that means it's a radio. And if we can turn the thing on and off in software very quickly, we can do on-off keying in software using the internal clock signal of this microcontroller. So that's what we did.
There's an antenna in that photo, by the way.
Yeah, this wire is our antenna, and it's carefully tuned. The way I decided on the length of the antenna is I reached into a drawer and pulled out a wire, and it was the first one I pulled out. But this was only done under. There's a reason we're not doing live demos of these, because
they work really well. They transmit at all kinds of frequencies.
Simultaneously.
On a little video, if you see, so he just runs the code and the light bulb turns on. It's a completely pointless thing to have to reach past your light bulb to turn it on using a piece of software. But some of these radios, I think, as Mike identified on the line a couple of weeks ago, he was designing one of these. Said, yeah, it works. It transmits as much as it receives, but it works. And it was not meant to be a transmitter. So here is our 433 megahertz. We'll get off with this. Start off with this one. 433 megahertz, just taking a clock signal, turning it on and off. But as we read up on this and we read the data sheet, we discovered that actually these things vary their clocks a lot. They have the ability to modify the parameters for the PLL on the fly. So we should, and I should say now, we have not got this working. We tried, and we can't quite get it. But we believe if we reconfigure the PLL on the fly, we can get frequency shifting out of this thing. And again, this is an off-the-shelf microcontroller. We do it on Great Fit because it's a board that Mike designed and we work on, and it's got a lot of cool peripherals. But this sort of hacking technique should be possible on almost any little microcontroller breakout board that you can go and buy. And a lot of these you can just go buy them from a chip manufacturer for $100 or so as an example dev board for them, and make incredibly noisy and horrendous radios. So I'll let you do the next one.
So that particular project that Dominic suggested that might have said something like it transmits as much as it receives. Well, here you go. This is my first in what I hope will be a series of breadboard SDR projects, like making the software-defined radio platform on a breadboard. And what I did was I realized, hey, we have a way to generate this clock that we're transmitting, that Mike Walters made that hack that we just showed you. Like, we can produce that 433 megahertz clock. What if I want to receive 433 megahertz? If I want to just receive 433 megahertz, well, the easiest way to do that is to generate a 433 megahertz clock and run it as a local oscillator into a mixer, right? And then I want to measure the output of that mixer. So what's the simplest mixer? An unbalanced diode mixer. One diode, one resistor on a breadboard. I use the exact same firmware that we did for the on-off keying transmit to drive my little one diode mixer. And then the yellow wire over there is I'm then measuring the current through that diode using an ADC, an analog to digital converter that's built into the microcontroller. It's not a very good ADC. It only operates at a maximum of about 400 kilosamples per second. Hey, but that's good enough for some things like narrowband transmissions, like narrowband FM, for example. So I was able to pick up a transmission from, from this little guy, right? Because if your radio doesn't speak Mandarin, is it really a radio? But I was able to pick up a transmission from this using the breadboard SDR approach. And we have a screenshot here. This is a little bit of a crude screenshot. We had to throw this together because I accidentally left my laptop at the hotel. But you can actually see down at the bottom is the frequency demodulated output. You're actually seeing the audio wave of me. This is the end of a transmission, and you can see there's kind of a burst on the left edge of the screen, and then a burst sort of in the middle of the screen. Those are me saying the last 2 letters of my call sign. And then at the very end, at the right-hand edge of the screen, you can see that little wiggle. That's the tone that the radio produces at the end of a narrowband FM transmission, right? So it totally works. It's crude. It's terrible performance. Like I have to transmit at 5 watts within a meter right, to make it work. But like it does work.
Okay, so now we're gonna take it up a notch into slightly more ridiculousness, if that's possible. Mike designed a board called the Opera Cake, which is its kind of development code name. We don't have a final product name yet, but it is this antenna switching board, and we're using it over on our booth to switch between different antennas as we sweep across a large portion of the spectrum, so we get the best view of the spectrum. But we've done this a couple of times, and we've tried some pseudo-Doppler direction finding things, and I was kind of looking for research projects in the lab, and I just said, it's got some use cases when it receives, but like, is there anything we can do with antenna switching when we transmit? And most of our ideas came out to like, well, if you control the radio signal going into the thing, then you control the radio signal, so what do you think the antenna switching board is going to do? And my answer was, phase shift key it. So what we do is we take this antenna switching board, we take loops of coax of varying lengths, specifically what we had in the drawer. But generally, you want lengths that vary by a half or a quarter wavelength. And then you use this antenna switching board with a CW going into it, and you switch rapidly between which signal path it's going to take, and you get phase shifts. And if you have your data signal controlling how the switching works, you get phase shift keying. And so this is something, again, because I'm using the lengths of cable that we had in the lab, this is not something I can show in front of you, because you really need to do it in a Faraday cage when we do it. What was the frequency of this?
We're doing this at 500 megahertz.
Yeah, 500 megahertz, which is not a thing I think I'm allowed to transmit anywhere. So inside a Faraday cage, as always. But what you can see at the bottom of the screen is we've got a phase plot out of this, and you can see we've used the cursor view in Spectrum here, and on these lines you can see a regular phase shift as I use my data signal to feed the switching, and all I've got is just a 500 megahertz CW going into the antenna switching board, and out the other side comes phase shift keying data. It is a thoroughly pointless way to produce phase shift key data, but I kind of love it. One of the things we wanted to experiment with actually was taking an off-the-shelf radio and feeding the output of that through this, so that we could like add a second layer of kind of signaling to some other kind of radio signal.
Sure, yeah, you could use that to like for a steganographic kind of effect, like hiding a signal in another signal. Right? You can introduce this phase shift keying modulation on top of some other radio signal that has a different modulation that otherwise might still be completely demodulated and decodable.
Exactly. Yep. Also, with the pseudo-Doppler direction finding, you're specifically looking at the phase shift to give you the direction of the signal. So if I can take my radio, add this antenna switching board onto the end of it, and intentionally mess around with the phase of the phase shifts in the signal being transmitted, then without affecting the reception of my signal, then I can hide from pseudo-Doppler direction finding techniques, which seems mean, but kind of fun, worth looking at. And this is, to be slightly controversial from what was said earlier,
Yes.
number of ADC bits.
Yeah, how many do you need?
One.
One? One ADC bit?
Yeah. And I'm going to let you explain why.
All right. All right. So, you know, as Steve mentioned earlier, like resolution, like the number of bits that your ADC gives you, doesn't really necessarily tell you the whole story. But in general, rule of thumb is like more the better, right? But what happens if you don't have very many? What happens if you have, you know, let's say a lowly 8-bit ADC like we have on RTL SDR dongles or on our HackRF? Well, if you capture at a very high sample rate, and then take every pair of adjacent samples, like 2 samples in a row, and add them together, well, what do you get if you add 2 8-bit numbers together? You get a 9-bit number if you average them. Well, same thing as adding them together. I mean, effectively.
Yeah. All right.
Like,
Sorry.
you get a 9-bit number if you add 2 8-bit numbers together. So every time you divide a sample rate in half in software, you can gain another bit of dynamic range. And that's a big deal if you have the capability to capture at a much higher sample rate than you otherwise think you need for the bandwidth of your target signal. So if you're able to capture at millions of samples per second, but your target signal only has bandwidth of a few kilohertz, well, you have many opportunities to decimate and gain, or divide the sample rate and gain dynamic range while decimating. And if we take this to the logical extreme, we should be able to make useful software-defined radios that have 1-bit analog to digital converters. And if any of you are thinking this is just ridiculous and completely useless, I would like to point out that actually 1-bit ADCs are fairly common in certain types of equipment, including GPS receivers. GPS receivers typically have 1 to 3-bit analog to digital converters in a highly specialized circuit that makes them work. And the reason they're able to work is because of things like being able to decimate to gain dynamic range. So we decided to take this to the extreme because we thought, well, if we're going to try to make the most ridiculous radios we can, wouldn't it be great to make one without even having an ADC? Like, no analog to digital converter. I just want to be able to use like a GPIO pin, a digital input that's either high or low, and use that as my analog to digital converter. Is that possible? Well, I don't have a radio to show you today, but I do have a demonstration that is a simulation that I've been working on. And I want to show you, I captured this file that's me. So this is GNU Radio. It's a visual flow graph. And I'm just going to walk you through the parts that are important. The first part is that I'm using a file that was captured with a HackRF.
So I just, can anyone read that, even from the front row?
Nah. Oh, that's cool. Hey.
There you go.
Thanks. Thanks, projector friend. So what I did was I captured a signal using a HackRF from my handheld, doing a little narrowband transmission, right? And so then I just saved that to a file. And then I wanted to simulate. Well, okay, I captured this 20 million samples per second with 8-bit quadrature samples. So 20 million times per second, I really get 16 bits. I want to throw out 15 of those bits and just take one of them, all right? One of those 16 bits. So that's what I'm doing, the top part of the flow graph here. There's this threshold block up here. And it doesn't really matter if you can see the details. The important thing to know is I'm throwing out Q. I have I and Q. I'm throwing out Q. I'm taking I and I'm thresholding it. And I'm just saying if it's high, it's a 1. And if it's low, it's a 0. And then I'm passing on that output and doing the decimation trick to gain dynamic range. And I'm capturing at 20 million samples per second, which is about like 1,000 times higher sample rate than I really need to capture this narrowband FM transmission. So 1,000 times, that's about 2 to the 10th power. So I should be able to like gain 10 bits of dynamic range. So suddenly my 1 bit turns into several bits, theoretically. Let's see if it works. So I will run this flow graph here, and this is just going to repeat through this loop. Is there a speaker on your? Is there a speaker in the house? Can you turn up the volume? Is that a thing?
Maybe.
Oh, there we go. Can you hear that?
Yes.
Yeah. Okay, so what you see here in the middle of the screen, you see that blue horizontal line? And you see how it turns into a sine wave when there's a transmission present? Right? Like that's the original signal from the hack RF. This nice, almost perfect looking sinusoid, right? And then the red signal that's overlaid on top of it, that's where I square it up. That's where I'm throwing out 15 out of 16 bits and I'm turning it into a square wave, right? And then I decode the thing and demodulate it, or I demodulate the thing, and then the top plot actually is showing the audio signal, which is the demodulated version, right? So it isn't super important that you hear it, but you can kind of visually see that top plot is, is showing me sort of the audio oscilloscope plot. Now one thing in this simulation that is kind of cheating is that I have a fine threshold with no hysteresis, right? So if it's over this threshold, it's a 1. If it's under this threshold, it's a 0. But if I want to use a GPIO pin on a like a microcontroller, it's going to have a high threshold that's like 2 volts and a low threshold that's like half a volt or something like that. I'm going to have a pretty big hysteresis that I have to overcome. So I added this little slider that lets me add a threshold, add hysteresis to this. And if I make the slider too high, there's too much hysteresis, you'll notice that that red line in the middle is now constant. My radio signal is too weak to overcome that hysteresis. But what if I add a little noise? What if I dither the thing? What if in the front end of my radio I just add noise? And so what I do is I have this other slider to add noise here. Now it starts sounding terrible, but so it turns out that we can make a perfectly useful radio with a 1-bit ADC. And according to our simulation, we should be able to do this even with hysteresis to overcome, as long as we can mix in some noise. Just add in some noise. Just like make a little noise diode circuit that just dumps some noise into the thing. I think that's pretty cool, and it's a project that I'm working on now to see if we can make this even more ridiculous. Go back to our slides.
I think
Or is
that
that the last of our
I think that was
slides?
the last of the slides.
That's where it's the last of our slides.
So I think, yep, that was
Alright.
the last of the slides.
Yes.
So
All right, thanks everybody. All right, before I get started, did anybody see this that Michelle was wearing? Y'all know what this is? Okay, so I put in a little plug for her real quick. So there's this whole community that does this thing called Badge Live. And at DEF CON, for example, every year they have a badge. And the badge has a microprocessor and a display and LEDs and lots of other stuff. There's typically a theme to it, a bunch of buttons on it. And part of the deal is to figure out how to make this thing do different stuff. And some people will take it apart and change the software on it and hack on it and all that kind of stuff. So they built one here that's it says Phase 4 Ground Trans Ionospheric Badge, and it's got an uplink and a downlink indicator on it, payload. It's a satellite simulation thing, and it's got a little screen on it and stuff. It's got a bunch of hardware on here. They're selling these for like $100 in booth 6203, and it's a really cool project. And if you want to get a young student interested in playing with electronics, this is a neat way to do it. And they have this one and another design over there. So if this interests you, feel free to go by their booth and take a look. All right, I'm Steve Hicks with Flex Radio, and I'm going to spend a few minutes talking about noise. And the thing that really got me interested in having this conversation is I talk to a lot of people about radios and noise on a regular basis and find that there's quite a bit of confusion about how noise works, how FFTs work, how noise floors work, noise figure, all that. So I have a bunch of questions here, and these are the kind of questions I get asked.
And so I want to throw these out there and then go through and answer some of these. Hopefully I have enough time to go through this whole talk. One of them is, why does the noise floor in my pan adapter drop when I change the pan adapter bandwidth? Get that one along. Is my radio out of calibration if my receiver noise measurement does not match my pan adapter noise floor? So in other words, if you look in a narrowband receiver and you look at the noise floor on the pan adapter, those two don't match. Why? I can see a signal in my pan adapter, but I can't hear it. My radio must be broken, right? Get that one. Let's see here. You're selecting a radio. Do you care about sensitivity, noise figure, preamp gain, or something else? Which of these things are important? Is there a relationship between any of those numbers? Your buddy is boasting about his rig's sensitivity, which is 3 dB better than yours. Is this important? Should you be ashamed in trade rigs? Has this ever happened to anybody in here? I know it has. Here's another one. I looked up the ADC in my direct sampling receiver. It says it has 16 bits with an ENOB, which is effective number of bits, of 12.3, and a 74 dB SNR, signal to noise ratio. I know there are 6 dB per bit of dynamic range. If I take 12.3 times 6, it's 74. Heck, even if I could use all 16 bits, 16 times 6 is only 96. My radio manufacturer says this radio has 105 dB of third order dynamic range. He's lying, right? That's right, that's right. Okay, so I want to talk a little bit about noise first, and then we'll answer some of these questions. So there's all kinds of noise that can interfere with radios, and here's a whole bunch of them. I'm not going to read all these out in the interest of time. But noise can be really complicated, and even those people that know noise well and deal with it every day can have challenging conversations about the nature of noise and how noise is affecting certain things. So none of this is simple stuff. Okay, so I have a pan adapter here, and I'm going to ask a question that people ask all the time to look at, and they say, what is the noise floor? And we often hear noise floor, and we'll point at it and say, that must be the noise floor there, but really, what is it? So I want to talk about this and use some analogies to do it. So I'm going to talk about the ADC and what it sees as a trough with or a bucket of water. And so if you take that water and split it into 2 troughs, the water level of that, presuming they're the same size, goes down by a factor of 2, which is, of course, 3 dB. Now, as I go through this, I want to point out that all my computations are done in the water domain, so you need to calibrate your calculators for that. All right, so let's say there's a diamond in the bottom of one of these troughs, and I'll give you as many bins as you want and as many sizes that are all factors of 2. How can you find that diamond? Well, one way to do it would be to take the buckets and split them all up. Let's say we take that water and split it across 1,024 buckets, each of which are 1,024th the size of the original trough. And now all of a sudden the water level is really low in all those, and the diamond sticks out above that. So congratulations, we've created the first water trough FFT, or the WTF FT. All right, so I want to kind of explain how this works and what's up with this. This is the equation that's going to govern this. This says that the noise behavior is proportional to 10 log base 10 of the bandwidth that you initially started with divided by the bandwidth that you ended up with. So this is what happens in an FFT receiver bin as we go down in decimation levels and show smaller and smaller bin size. So the noise is reduced by this amount. So you can think of an FFT as a series of S meters stacked on side end next to each other. Does this make sense? So if you look at the pan adapter in a typical radio, you see the signals bouncing up. Think of that as a bunch of horizontal S meters that have been turned on their side, and they're jumping up and down. And each one of those S meters is the width of the bin of that pan adapter FFT. So the more bins that you have, as we showed in the water trough FFT, the less water's in there, the noise goes down, and then you can see further down in there, and that's what allows you to see into the pan adapter. So in the example that I showed before, we had our 1,024 bin WTFFT. We reduced the bin by 10 log base 10 of 1024 over 1, which is 30 dB. So that lets me see 30 dB below where I can normally see in my full bandwidth. All right, so in the case of this, you might ask, well, why does the noise go down, but the level of the diamond, which would be my signal, does not? So if your signal is contained within the context of a single bin, as you zoom in further and further and make that bin smaller and smaller, all of the energy from that signal remains in that single bin, and so it doesn't go away. Whereas the noise, if it's evenly distributed, continues to go down and be split along all the bins because that noise exists across all frequencies and you get to divide it out by frequency. Does this make sense? And that's the reason I used water as an example, is because it's like that. It's fluid and flow across things. Okay, so if you split the signal evenly across two bins, it reduces it by 3 dB in any one bin. So this says if you've got a signal and it's a strong signal and you happen to narrow your bins small enough that it begins to cut into the signal and have the signal cross multiple bins, then it will start to go down as well. And for the pedantic people in the room, yes, we're ignoring window leakage, scalloping, and all kinds of other effects in DSP stuff here. So this is an example of that. This is a WSGT8 signal. On the left, I've taken little slices out of the pan adapter here. On the left is one where I'm zoomed way out and my bin size is large. It's tens of kilohertz and my quote-unquote noise floor is very high because I've got lots of water in my troughs. And as I begin to zoom in further and further, all of a sudden this signal pops out because it's still a very, very narrow signal and it's contained in one bin when I get down to the end here, but my noise floor drops. And this is how your FFT is allowed to see quote-unquote below the noise floor. All right, does this technique ever not work? Yes, it's when the noise is not evenly distributed, and it's not average white noise. If you have a frequency-dependent noise source, so if you've ever seen like a switching power supply noise or something like this in your pan adapter, as you zoom in, eventually that noise is going to be contained just in those bins, and it's not going to go down for you. And of course, if you have those kinds of noises, we have special tools to deal with them based on the type of noise it is. Is it an impulse noise? Is it whatever kind of noise? All right, so let's go back to these questions. Why does the noise floor in my pan adapter drop when I change the pan adapter bandwidth? Well, we just showed that. We reduce the noise by 3 dB each time we reduce the bandwidth by half, and that lets the noise go down, and you can see down into the noise. This is the fundamental principle behind WSJT and all the weak signal modes, is we use time to integrate, and we use narrow bandwidths to integrate and be able to see a signal that is quote-unquote below the noise floor. If you've ever run any of those modes, there's a column in there that tells you what the signal-to-noise ratio is, and it's negative, right? How could it be negative? How could the SNR be negative? It's because those signals actually are below what we call the 500 hertz noise floor. That's what we talk about as amateurs. All right, is my radio out of calibration if my receiver noise measurement does not match my pan adapter noise floor? How many people have an SDR and have seen this? You look at the S meter, and the S meter doesn't match the noise floor in your pan adapter. No, you need to look at, in order to understand this, you need to look at the difference in the receiver bandwidth, which is your receiver you're listening to, the narrowband receiver, and the pan adapter FFT bin bandwidth. So those two things have to be equal in order for the noise floor to be the same, because again, they're like these water troughs, and if you have one that's big and one that's small and you're pouring the noise across them, they're going to be different. So if you really wanted to look at this and understand it and compare and see if things were properly calibrated in your SDR, what you would do is make the FFT bin size the same as your receiver noise floor, as your receiver filter size in your receiver, and then those will be equal. All right, I can see a signal in my pan adapter, but I can't hear it. My radio must be broken, right? As we just talked about, no, a good FFT is generally a much better instrument than your ear and brain when the bin size is small. So all of us have probably heard CW before in a 1 kilohertz bandwidth. And you hear the rushing sound along with the CW. Your brain is pretty good at picking out the CW signal, the single tone, and rejecting most of that noise. You can listen to it, you can hear it and say, yes, I know there's 1,000 kilohertz noise in there, but you can go pick that out. But at some point there, the FFT is better than your brain. Like the ultimate bin size on one of our radios is around a hertz, and your brain is not that good, and we can see below where you can hear it. So that doesn't mean there's something wrong with your receiver, it just means that the instrument is better than your ears. Okay, so let's play quiz time here. Assuming your signal strength in your 500 hertz receiver, which is what we usually talk about as amateurs, noise only says minus 100 dBm, and your pan adapter shows minus 120 dBm, can you determine your FFT bin size? Well, we can use the same equation and say the answer is a 20 dB difference in signal, and we know that we're 500 on the slice receiver, and we want to know what the bin size is, and you go calculate that and say, yes, my bin size is 5 hertz. So you can use this equation to work both ways and understand how your receiver works. So if you have an SDR, go play with this and mess around with it and get an intuitive feel for how this stuff works. It's useful to understand it. So noise floor issues haphazardly kind of in our business. Most of the radio vendors in the ARL, when we talk about noise floor, we mean noise floor in a 500 hertz bandwidth. The noise floor will go down as the bandwidth is reduced. So if you decimate, if you reduce your filters, any of that kind of stuff, it'll decrease the noise floor. And again, WSJT, CW, all of that, those modes take advantage of that. So if somebody tells you they heard a signal 12 dB below the noise floor, this is what they're telling you. They're saying they mean below the 500 hertz noise floor. So their detector and their filter receiver is only 10 hertz wide. They're hearing the signal actually 5 dB above the noise floor. All right. So now when somebody comes in your shack and they see your SDR, I saw the hands, I know all of you have an SDR, and they say, that's pretty neat, what's the noise floor of your receiver there? You're going to go, now I got to think about that a minute, because I know some more stuff now that I didn't know before. Okay, I looked up the ADC in my direct sampling receiver. It says 16 bits, blah, blah, blah. My radio manufacturer says it has 105 dB of third order dynamic range. He's lying right. Well, let's calculate that. So let's say that this receiver is sampling at, let's say we looked at 12.4 bits of effective number of bits. That's at the full bandwidth of the converter. So when you go buy an ADC and they specify the ENOB, they're talking about the full bandwidth of it based on the sampling rate that you're running it at. And so let's say we're running that converter at 100 megahertz, which is not an atypical speed to run it at in an HF radio. So now we can go use the same equation. Let's say we're looking at 48 kilohertz receiver, and we have 30 dB or 33 dB of processing gain. So we can take that and add that to our 74 dB of dynamic range that the converter has in the full bandwidth, which gives us 107 dB, which is an effective number of bits of 17.8. And that tells us, if you go run some other math, that there's about 21 bits that are actually toggling here. So you get processing gain. It's again what Michael talked about with the 1-bit ADC by oversampling. So this is what we do in most radios. We oversample, and therefore we get higher performance out than what the converter's rated at the bandwidth that it's rated at. And the summation is, of course, no, he's not lying. Well, most of them are. All right. Let's see. I got a few more minutes here. I'll spend a little bit of time talking about this. I see a lot of people make mistakes on 6 meters because you find 6 meters in an HF radio. People think it's HF. The coax is not really important, all that kind of stuff. But 6 meters is really VHF. So I want to talk about how things can go awry on 6 meters. So let's say you bought a 6 meter radio with a stated noise figure of 5 dB. And you can go look this up on a manufacturer's data sheet. If they don't tell you what the noise figure is, you can go calculate it. What is the noise floor of that receiver going to be on 6 meters? So I have some choices here. Any ideas? All right, well, it's a trick question. The answer is there's insufficient information. And the reason is because you don't know what bandwidth you're measuring it in. So I'm going to give you a golden rule here, which for the purposes of our stuff will help you. A 0 dB noise figure at room temperature is minus 174 dBm in a 1 hertz bandwidth. And so this applies for all SDRs, and this is something you can use to go figure this stuff out with. So we're going to use this equation. I hope this isn't too mathy. The good thing is that we're taking this, so if you want to go back and follow math, you can do it. All right, so we take minus 174 dBm plus the noise figure of the receiver plus the dB bandwidth difference from 1 hertz, and this will get you what you want to know. So for example, a receiver with a 5 dB noise figure and a bandwidth of 500 hertz has a noise floor of, we take the minus 174, we add the 5 dB. Since we're in 500 hertz, we have to calculate that essentially in dB. A kilohertz would be 10 to the third, which in dB would be 10 plus 10 plus 10. Since we're at 500 hertz, we're 3 dB less than that. So you get 10 plus 10 plus 10 minus 3. You run that stuff all out, you get minus 142 dBm. So that's where it would be in a 500 hertz bandwidth with that noise figure. Okay, so here again is that useful equation that you'll need. Okay, so there's another useful equation called cascaded noise figure that lets you calculate what all of your equipment's going to end up with in terms of noise figure. And here's this one. I'm not going to go into this in any detail, But I'm going to tell you there's a lot of cheat sheets that you can use on the internet to go calculate this stuff. So let's say you've got a 10 dB noise figure receiver, and it's got a 5 dB preamp on it, because everybody wants to run a preamp on 6 meters. And the noise figure of the preamp is 5 dB, and it has 10 dB of gain. What is your final noise figure in your receiver? So you can go plug this in. I think this one I got on Pasternak Enterprises website. If you go search for cascaded noise figure on the internet, there's a bunch of these calculators. I guarantee that at least 3 out of 5 of them will give you the correct answer. So you can go try a few of them and then average the numbers out and figure out what's going on. All right, so here's a pop quiz. You're going to buy your spouse a 6-meter radio for Christmas, right? And so we got 3 radios here, and here's the option, because it's the Magic Band, and you guys have Magic in most of them. So here's the 3 choices. We've got radio 1, radio 2, radio 3. Here's the sensitivity of noise floor in 500 hertz. I got minus 136, minus 123, minus 139. Here's the noise figure, and those two are the same thing, just expressed differently. So one's got a 13 dB noise figure, one has a 24, one has an 8. And then that radio happens to have a preamp in it. And so these are the 3 different preamps that are available, one on each radio, 5 dB noise figure with 10 dB gain, 2 dB noise figure, 30 dB gain, and 7 dB noise figure, 20 dB gain. Which radio should I buy? Which one's going to work best on 6 meters? Which has the best noise figure? Who knows? Generally what I hear is don't get the one with the bad noise figure. Don't get the 24 dB. It has horrible sensitivity. They'll look at the sensitivity number and say, oh, it's horrible. We don't want that one. All right, so let's go calculate. We have this handy dandy tool. We know where it is on the web now. Let's go plug the numbers in. Okay, so the first one we look at and we say we got a 5 dB noise figure preamp with 10 dB gain on a 13 dB receiver. So you see where I plugged in all those? Each one of these lines across is a stage, and the final one is going to be the noise figure of my receiver with no gain. So I plug all that in, I hit calculate, and it says the final noise figure is 7 dB on the first one. The second one, which had the horrible noise figure in the radio, 24 dB, I had a 2 dB noise figure gain amplifier with 30 dB of gain. You calculate this and it's 2.6 dB. So it's much, much better. And the final one, I had an 8 dB noise figure receiver. I used a 7 dB noise figure preamp with 20 dB of gain, and I get 7 dB. So this says that the middle one, the one that had the quote-unquote worst sensitivity, is the best receiver of the 3 on 6 meters. How can that be? The deal that the cascaded noise figure equation really shows you is that the first preamplifier, the first gain stage in there, really sets the noise figure of the receiver. And so if you play around with the equations, you realize that's the case. And this is why guys that run 6 meters and do it well often will put a mass-mounted preamp with a low noise figure up on their antenna right up next to up on the tower next to the antenna. All right, so you know all that. Okay, you figured out your radio with the preamp has a 6 dB noise figure, let's say. You run coax from your radio to the tower and up the tower to your 6-meter antenna. You're using 180 feet of LMR 200 from the rig to the antenna. What is your system noise figure? All right, so coax you can look up. You go to the manufacturer's side. Here I went to times microwave, because LMR is times microwave. 180 feet of LMR 200 at 50 megahertz calculates out and says it's 4.5 dB of loss, including the connectors. So you can go use the same web page again. You plug in 4.5 dB for the noise figure of the coax, minus 4.5 dB for the gain, 6 dB noise figure for your radio, and it says now you're at 10.5 dB noise figure. So you kind of screwed up your noise figure by running that coax on it. Okay, your system noise figure is 10.5 dB. What now? You could use a mass-mounted preamp. What's another choice? You could use better coax. So those are 2 things you could do. Here's an example preamp. It's less than 1 dB noise figure with 15 to 20 dB of gain. Well, wait a minute. Now I don't know how much gain to use. The amplifier is variable. So let's look that up. Again, you can plug all this stuff in an equation. So you realize your coax is killing you. Add a mass-mounted preamp with a 0.8 dB noise figure and 10 to 20 dB of gain that's adjustable. Where do I set the gain? Should I use 10 or 20 dB? Right, this is the common answer. Turn it up. Is there an 11? Turn it up. Right, so let's go calculate it. We'll go plug it back in here. Okay, on the left we've got 0.8 dB with 10 dB of gain, 4.5 dB coax loss, and then our 6 dB guy calculates out to 3.5 dB noise figure. On the right-hand side, run the same thing, but with 20 dB gain, and I get 1.2 dB. So I have a, what is that? That's a 2.3 dB better noise figure by cranking the gain up to 20. Was that the thing to do? Maybe. Here's the deal. Only the noise floor, well, see, you only want to lower the noise figure of your system a little bit below where the atmospheric noise floor is. Anything else beyond that is overkill and it's going to lower your dynamic range. So let's see here. We talked about this. We said it's 2.3 dB. But what happens is, at the high end, because you've added an additional 10 dB of gain, the overload point of your ADC is some fixed number. Let's call it 0 dBm. When you put 10 dB of gain in, that slides that down by 10 dB. So if it was 0 dBm, now it's minus 10 dBm. So you picked up 2.3 dB at the bottom, but you lost 10 dB at the top. So your net is minus 7 dB. Does this make sense? This is a graphic to show you what this looks like. So the before picture, you have all this green bar, which is your total dynamic range. So maybe your overload is at 0 up there, and down here, here's your 2.3 dB, your 3.5 dB noise figure. When you added the 10 dB, you took 10 dB right off the top with that gain, and you only gained yourself 2.3 down here at the bottom, so you have a net loss of dynamic range of 7.7 dB. Is it worth it? Well, it just depends. If you have signals that are strong enough to overload your radio, it was a bad choice. You're going to go into overload and you didn't need to do it. If that's not the case, then yeah, sure, why not? So how do you really know what the noise figure is that you need? You can look at this. How many people have seen this chart before? Yeah, okay, that's good. I'm glad to hear that. So this does not have 6 meters on it, but it shows 0 to 30 megahertz, what the typical residential, rural, and quiet rural noises are in atmospheric noise. So you can see you go down to 160 meters and the noise is just horrible. Why is that? Why is the noise bad on 160 meters? Because it can propagate all around the world, and you just hear everything from the man-made noise of all kinds of stuff, and it propagates well. You go up to 30 megahertz, the band's open on 10 meters all the time, right? So that's where all that noise comes from, which is not much. All right, let's see here. Your buddy's boasting about his rig sensitivity, which is 3 dB better than yours. Should you be ashamed and trade in rigs? No. There's lots of other factors that should be considered when comparing radios. Preamps, ergonomics, RMDR, reciprocal mixing dynamic range, the dynamic range of the radio, all kinds of stuff. So do not go choose a rig based on a single performance metric, especially one that you don't fully understand. You want to read about it and understand what's going on and all that kind of stuff. Okay, that's all I have. We have 15 minutes for questions, so all these guys can come up here. You guys raise your hands and ask any of those questions, and we will try and answer them. Here we go.
I'm still confused.
Okay. To see a waterfall, all of the SDR rigs made by all of us and probably most of the other guys all have hand adapters and waterfalls on. If you want to get started and you want to play around with SDR and just understand it, go buy a cheap one and figure out how to do it. Our radios are high performance HF radios for guys that want to buy an HF radio that happens to be an SDR. So it depends on what you want to do. This is what we're all saying up here. Yes. No, there's no reason to do that. This is like saying I have an old a large format camera, a 2x2 camera, right? And I would never have you throw that away when you buy your DSLR. The DSLR has advantages, but your wide format camera does too. Yes. Typically, no. You typically don't use your old HF radio to do SDR. Other questions? Yeah.
Many of the radios have a setting for dither, format dither.
Yes.
Is that really necessary in a ham radio setting where you're going to have a relatively high noise floor from the surround level noise from the ADC?
It's a great question. I wish I had something handy for asking that question. Okay, the question was, a lot of the analog digital converters have a dither function in them, and that dither function has been exposed at a high level in the software. Is that really necessary on today's ham radios, especially when there's noise present in the ADC? Okay, so first of all, let's talk about what the function of dither is. If you take a beautiful sine wave created out of a generator that doesn't have a bunch of noise in it, as that sine wave crosses the bits in your converter, it will create quantization noise, which will show up as spurs in your ADC output. You'll see them in your pan adapter, that kind of thing. This is largely a instrumentation issue. If you go test a radio in the lab, you will see that kind of stuff. When you take a ham radio and you put it on the air on an antenna, there is typically enough random noise that will override that. So if you think about a really strong signal, which is where you want to get your dynamic range, and there's a little weak signal that's present with it, and you look at that in the time domain, you'll see this huge sine wave at whatever the voltage of your converter is, 2 volts, peak to peak, and riding on top of it is this little noise on top of it, right? And so the net effect of placing your radio on the air is it has all kinds of noise on top of it, which randomizes the radio and generally causes that not to be necessary. But it depends a lot on the converter and how the radio is designed and all kinds of other stuff. So in a testing environment, if you're testing it in a lab, you almost always need the dither in order to make the radio look good in a laboratory environment. But I think in a real environment, generally, it's not going to help you a lot. As long as you have more than one bit. Yes. Good point. Good point. Okay, other questions? Yeah.
Do you know if there's any like serious or focused efforts to do a GRC to HDL, the HDL converter? I see little talk here and there, but I don't see anybody really pursuing it.
Okay, so the question is there a GNU radio to HDL kind of converter to go do that?
And really, it would have to be from GRC unless you really want to parse the Python. Frankly, I wouldn't want to. So.
Yeah. I don't know of anything that's doing that. You know, Edis has a RF knock. Are you familiar with RF knock? So RF knock is kind of some I'm going to totally butcher what it does because I don't know it real well. But my understanding is it's some kind of prepackaged RF pieces that you can piece together, I think using GNU radio, and it will go generate the necessary stuff in HDL, but I think some of it's prepackaged for you. So there's some stuff like that, but I don't know of any direct compiler kind of thing where you would start out and say...
Right, one other option is, you know, RF toolbox, simulate, encoder, and that just is change.
Yeah. Yeah, well, I will say that for most things that most hams want to do, we want to deal in narrow bandwidths anyway. We're not talking about wanting to actually decode something at 20 megahertz. And so the FPGA is not really necessary. You can use the FPGA to do the down conversion and get you a narrowband receiver. Once you have a narrowband receiver, you can do all the processing in a general purpose computer doing whatever you want using, you know, flow graph generated Python or whatever else. So, but I don't know of anything like that.
Okay.
As you approach the 1 bit limit, and then as you try to increase the bandwidth or increase the quality of the signal, is there a limit to what the oversampling will give you? Is there a limit to how high your oversampling can give you? So as you're developing the audio signal on a very narrow band signal, could you get a wider band signal if you had a whole bunch more oversampling? And is there a limitation to how far you can go with that?
Well, if you go talk to ADC vendors today, they're probably going to tell you, yes, we have a limit today, but we're pushing it every day because the rates on the ADCs are going up and up and up and up. But as Michael pointed out, as you go, if you go look and just go pick some random ADCs, go to Analog Devices or TI or any of the manufacturers and look up an ADC, and they'll say, this ADC is at 250 megasamples, and it's 16 bits, and it's got 12 dB, 12 bits, Then you go look and say, oh, well, they've got one that samples at 2 gig. And it's going to be a proportionally less number of bits typically, so that if you decimate down, you're going to end up in about the same place again. That's been my experience. Now, there's certainly variation in that, but you're not going to go find a 6 gigahertz ADC that samples at 16 bits and gives you 13 bits of effective number of bits. It's not going to happen. There's nothing like that today. Now, there may be in the future, but do you have any other comments on that?
Yeah, I just want to add one thing. Like, yeah, in theory, you can totally just sample at, a tera samples per second, no problem, right? Like, but there's a limit to the ADC manufacturing, how high they've been able to go in their sample rates. But also, the thing that you might not consider right away is that the ADC does not produce a clock out of thin air. It's clocked by, it has a sample clock that has to be generated somehow. And how are you going to, okay, let's say a manufacturer comes out with a terasample per second ADC that we can buy tomorrow. That's great. How are you going to clock the thing? And how much, you're going to decimate your laser. I like that. I'm going to suggest that to our new intern who's starting on Monday. He might know a thing or two about that. But it's going to, you have to have a way to generate a clock, and that clock has noise characteristics that affect the output of the ADC. And generally speaking, the higher the frequency of the clock you're going to go, the worse noise performance you're going to have in that clock, and that's also going to affect the ADC. So yeah, the theory is you can just oversample without limit, but in practice we're limited by the performance of the ADCs and the performance of the clocks that drive them.
There's also some other tricks that ADC vendors are playing, which interleaving is one of them, where you want to sample at twice the rate. You can use two ADCs that are phase shifted, and they each sample, this one samples, and this one samples, this one samples, this one samples. And so they're starting to put more of those things in the dies, and so there are some things you can do to go up and not lose a lot of capability. Other questions?
These guys over here, so I enjoy this jet streaming, sharing the radio signal out on the web. And so Web SDR, he's the only guy that seems to be able to do 0 to 30 megahertz and have multiple people connected to the server and not hijack other signals, right? So he can have 500 people listening to the server, but none of that is available to us. Will we ever see something where we can have something similar to the guy, the creator of Web SDR, where you have multiple people connecting, each with their own individual stream on a home server? I think it's not any of us, but go ahead.
I was just going to say that if you go calculate the bandwidth required to do that, this is one of the real problems. And so I think today that's one of the practical limits of doing that, but I have no doubt that that's going to be, as we go forward in time, more and more of that stuff's going to show up. Do you have anything more to say?
There is one open source, so the question was about Web SDR, and Web SDR is a pretty cool thing, but it's not open source. It's like a single implementation, and I've heard that you can get some code if you ask, real nice, but it's not open source and published, so anyone can use it. And but there is an open source project that has some similarities to it called OpenWebRx. But I think that the fundamental characteristic that you're interested in here is taking a single high bandwidth stream, sample stream, and then making that available, making multiple down converters off of that stream available to multiple users. That's something I haven't seen yet in the open source world, but it's definitely possible. And if I were to sit down and try to create that feature in some existing software today, where the place I would start would be OpenWebRx.
Any other questions? All right, thank you all. Have a great day.